Welcome viewers. In our session for today, we are going to discuss about finding the Laplace transform of a function f of t is equals to t using the first principle. And when it comes to the first principle, the first thing that you need to understand is about the first principle formula. As we understand and know that the Laplace transform of our function f of t is equals to integration with respect to our limits exponential negative st multiplied by our function f of t, and our integration is with respect to dt using the first principle. Now from this point, what we need to know is that the Laplace transform of our function f of t, the function f of t is equals to t, and this one is going to be equals to integration with respect to our limits exponential negative st we multiply by our function t, and our integration is with respect to dt. Unlike other forms, when we reach at this point, we were converting sine into an exponential, cos hyperbolic into an exponential, or sine hyperbolic into an exponential. Here the term of t we are not going to convert into an exponential, or rather we are going to use the integration by parts formula. When it comes to the integration by parts formula, we know that an integral of our term u dv with respect to dt is equals to uv we subtract from an integral of v du with respect to dt. When you come here, we have our limits, to mean that once we've worked out this part, we are going to insert our limit, and here we must have our limit. Once you've understood the formula, the next thing that we need to understand is that between the exponential and the trigonometric function, which is the algebra, here which one becomes the u and which ones become dv with respect to dt. By understanding that, we have this acronym where we have this one will help us in understanding which term becomes our u and which term becomes dv with respect to dt. We just don't select randomly, whereby this one is an exponential function. Here this one is a trigonometric function. This one are the algebraic function. Here we have the inverse function, and lastly we have the logarithmic functions. Now here we have a trigonometric function, we have an algebraic function t, which is a letter, and an exponential. Since t is here, it will always take a u, to mean that if you can be told to integrate, let's say, cos 3t with respect to t, and our integration is with respect to dt. Here we have a combination of this one here is an algebra, this one here is a trigonometric function. Which one will take a u, which one will take a dv with respect to dt? When you come here, you will find that the algebra, which is a t, comes before the trigonometric function, which is cos 3t, to mean that cos 3t automatically will be dv with respect to dt. to dt. And that is how you select between which one becomes u and which one becomes dv with respect to dt. Once you understand this, now here we are going to have our u will be equals to, we say that our u is going to be an algebra, and the algebra here is equals to t. Our dv with respect to dt, from here we are going to have exponential negative st. Our term of u, we always do a differential of it. Du with respect to dt, we are going to have, when we differentiate that, we are going to have 1. And on this term, we are going to do our integration so that we can have our v, which is equals to exponential negative st all over negative s, since we are going to have our integration with respect to that. Now let us get back into our working, because we have all the function that we were requiring, that we were in need of to do our working. So we understand that the Laplace transform of our function f of t is going to be equals to, here our u is equals to t, our v is equals to exponential negative st all over negative s. Our integration is with respect to our limits. We come and subtract from an integral of v. Our v is equals to exponential negative st all over negative s. We multiply by du with respect to dt, which is equals to, we multiply by 1. And here our integration is with respect to dt. Now let us do our working out here and carry out our working here. By carrying out our working here, we are going to insert our limits. The Laplace transform of our function f of t is going to be equals to, we are going to start with the upper class limit, whereby we are going to have an infinity exponential negative infinity all over negative s. We subtract from the lower class limit, we are going to have 0 exponential negative s of 0 all over negative s. We subtract from this side, we are going to do an integration, and by taking our integration here, we can come and factor out this. When we integrate the exponential, we are going to have exponential negative st all over negative s. And here our integration is going to be with respect to the class limits. At this point, we are going to have 0, 0 multiplied by that, we are going to have 0. So these two are going to cancel out, and automatically here we are going to have a 0. To mean we are going to have the Laplace transform of our function f of t is going to be equals to, these two will cancel out to be a 0. This one multiplied by this, we are going to have 1 all over s. We multiply by 1 all over a negative of s. We factor out that. We come and get to have exponential negative st, and our integration is with respect to the class limit. Let us now insert here our class limits, whereby we can have the Laplace transform of our function f of t is going to be equals to 1 all over negative s squared into exponential negative s. We insert the upper class limit to the term of t, we are going to have infinity. We subtract from exponential negative s, we come in and insert our term of t there. From this point now, we understand that the Laplace transform of our function f of t is going to be equals to, here we are going to have 1 all over negative s squared into exponential raised to a power of an infinity. We are going to have 0, we subtract from, this one is going to be 1. This negative is going to affect whatever we are having there, and we can come and now have the Laplace transform of our function f of t is equals to 1 all over s squared. To mean that the Laplace transform of our function t is equals to 1 all over s squared. And this is how you go about finding the Laplace transform of our function f of t is equals to t. Now let us discuss about finding the Laplace transform of a function f of t is equals to t squared and have a comparison between the two. In this session now, we still want to use the first principle in finding the Laplace transform of a function f of t is equals to t squared using the first principle. And we all understand when it comes to the first principle, the first thing that we need to understand is about the first principle formula. And the first principle formula, we know that the Laplace transform of our integration with respect to our limits exponential negative st we multiply by our function f of t, and our integration here is with respect to dt. To mean that after noting down the first principle formula, we come and replace our function f of t with t, to mean that the Laplace transform of our function t squared is equals to integration with respect to our limit exponential negative st we multiply by our function t squared, and our integration is with respect to dt. From this point now, we are going to differentiate whatever we are having. We are going to integrate, we are going to integrate whatever we are having here. We know that an integral of u v dt is equals to uv, we subtract from an integral of v du with respect to dt. When we come to our integration, we have our limits, to mean that here after taking our integration we must use our limits, and here we must have our limits. We agree that for us to come up with our terms of u and our terms of dv dt, we must use this acronym, whereby this one stands for the exponential, trigonometric function, algebra, inverse functions, and the logarithmic function. And we agree that the term, for example here, we are having our term of t as an algebra and an exponential. Our term of t is going to be equals to u, and here our exponential is going to be equals to dv with respect to dt. To mean that we are going to have u is equals to t squared, and our term of dv with respect to dt is going to be equals to exponential negative st. Our term of u, we are going to do differential of it, which is going to be 2t. Our term of dv with respect to dt, we are going to have an integration of this one. And when we integrate whatever we are having here, we are going to have v, which is equals to negative st all over a negative of that. Now at this point we have whatever we were looking for, so as we can simplify we can use integration by part to simplify whatever we are having here. Let us now get into our working, whereby the Laplace transform of our function f of t now is going to be equals to, here our u is equals to t squared, our v is equals to exponential negative st all over negative s. We come and insert our limits. We subtract from here an integral of that with respect to our limits, an integral of v. Our term of v we understand exponential negative st all over negative s. Du with respect to dt is equals to 2t. And our integration there is with respect to dt. At this point now, the Laplace transform of our function f of t is going to be equals to, we are going to insert the upper class limit at this point, and by inserting the upper class limit we are going to have, where we are having t, we are going to have our upper class limit, which is infinity squared. We multiply by negative s into infinity. This one is going to be all over negative of that. We come and subtract from the lower class limit. The lower class limit is going to be 0 squared exponential. Here we are going to have negative s 0 all over a negative of s. Now we are done with our class limits in this bracket. We come and subtract from, here we can come and have 1 all over negative s, an integral with respect to our limits. Here we are going to have negative s 2t, and our integration is with respect to dt. And infinity multiplied by everything, here we are going to have 0, 0 multiplied by everything, there we are going to have 0. So we are going to have the Laplace transform of our function f of t is going to be equals to, here we are going to have 1 all over s, an integral with respect to our limits, exponential negative st, we multiply by that 2, we can come and factor out, and here we are going to have 2t, and our integration is with respect to dt. Here also we are going to use integration by parts in simplifying whatever we are having here. And by simplifying whatever we are having here, we are still going to use the same formula and the same acronym, whereby our term of u is going to be equals to t, our term of dv with respect to dt. From the formula here we are going to have exponential negative st, and lastly here our du with respect to dt. Because we agreed on the term of u, we do our differentiation, we are going to have 1, and here we are going to do our integration. Here we are going to have exponential negative st all over negative s. Let us now get back into our formula, whereby we say that the Laplace transform of our function f of t is going to be equals to u. Our u now here, because we are working whatever we are, because we are simplifying whatever we are having here, our term of u, we agree here u is equals to t. Our v now is going to be equals to exponential negative st all over negative s. we come and have our class limit, we subtract from v, an integral of v. Our v is equals to exponential negative st all over negative s du with respect to dt is equals to 1. And everything here we were multiplying by 2 all over s from our first working. This first bracket is going to be 0 because we are going to operate it just the way we've done this one, whereby our term of t we are going to replace with the upper class limit, our term of 0, our term of t on the other side we are going to replace with 0 on the lower class limit. And now here we are going to have the Laplace transform of our function f of t is going to be equals to s all over this one. When we multiply by this is going to be a positive, so we are going to have s squared, an integral with respect to our limits, infinity up to 0, exponential negative st, and our integration is with respect to dt. From this point now, we can carry out our integration here, and we are going to have the Laplace transform of our function f of t is equals to 2 all over s squared. In here we are going to have exponential negative st, and our integration is with respect to our limits. This one is supposed to be a negative because here we are carrying out our integration. Now, the Laplace transform of our function f of t is going to be equals to 2 all over a negative s cubed into exponential negative st. We have our limits. We've only factored whatever we are having here out. Let us insert our limits here. So we are going to have the Laplace transform of our function f of t is equals to 2 all over negative s cubed. We multiply by exponential negative s. We insert the upper class limit. We subtract from exponential negative s. We insert the lower class limit. And here we are going to have the Laplace transform of our function f of t is equals to 2 all over negative s cubed into, here we are going to have 0, here we are going to have a negative of 1. And this negative is going to affect whatever we are having here. Hence we are going to have the Laplace transform of our function f of t is equals to 2 all over s cubed. And this is now the Laplace transform of our function f of t. In conclusion, we can come and say the Laplace transform of our function t is equals to 1 all over s squared. To mean that the Laplace transform of our function t squared is equals to 1 all over, 2 all over s cubed. In case we were supposed to carry out a Laplace transform of our function t cubed is going to be 3 all over s to a power of 4. In short, we can come and say the Laplace transform of our function t raised to a power of this is equals to n, whatever we are having on the power, all over, because when you check here, we were having power 1, here is 1, power 2, here we are having 2, power 3, here we are having 3. s, and here we are going to have n, we come and add to 1. Because when you check here, we have a power of 1, and here we are having a power of 1 plus 1, which is equals to 2. Here we are having a power of 2, to mean that here we are going to have a power. That power we add to 1. Hence, we can come and say the Laplace transform of our function t raised to a power of n is equals to n all over s raised to a power of n we add to 1. Thank you for your time. Let us meet in our next session.